La dará Rafa Guzmán. Rafa Guzmán es profesor de investigación actualmente de Cantabria, del Instituto de Física de Cantabria. Rafa también es, de alguna manera, el investigador principal de la primera misión que está liderada por España, a la que ya pertenecen más de 130 personas en el consorcio, con una tercera parte, por tanto, casi unos 40 científicos y ingenieros españoles trabajando en la misión. Gracias, Pablo. Gracias.
Bueno, en primer lugar, buenos días. Muchas gracias a todos y especialmente a Minia y al comité organizador por invitarnos a compartir este sueño de esta misión con todos vosotros. Para mí me hace mucha ilusión estar aquí hoy porque realmente este sueño comienza en una misión de la SEA hace 14 años, allí en Madrid, tras una conversación con Carlos Frank. Y realmente os digo que es muy emocionante el estar aquí hoy cuando ya estamos metidos de lleno en la misión. Es difícil competir con Pablo y su charla sobre Euclid, pero intentaré hacer lo mejor posible. So switching to English now. ARRAKIHS was selected as the next F-class mission by the European Space Agency in November 2022 after a very competitive process. We were 19 proposals from all over Europe. There were 2 different phases, 3 different interviews by committees, 1 engineering committee at ESA, 2 scientific committees. And in the end, we got actually the good news that we have been selected as the next F-class mission. F for fast, but for us is more like a fast and furious, because for the last for the last year and a half, for people like Santi Serrano, for Maria Angeles and Elena, and the entire team, actually, it feels already like a 10.5 years. It has been extremely strong pace of work, but we feel extremely delighted, actually, to share with you these results. So in a nutshell, the F-class mission at ESA guarantees a budget of about 175 million euros from the European Space Agency. And they are responsible for the spacecraft, for the launcher, and also for the mission and science operation centers. Now, we in the consortium, we are responsible, well, the consortium is led by Spain, and the original consortium included Switzerland and Sweden, Austria and Belgium. And now this year, we have the opportunity to include the UK and Denmark, Norway and Portugal. In addition, we have a few institutions from Holland and Denmark, plus the United States and Taiwan and Thailand. Now, in Spain, the mission is being led by IFCA in Santander, with a major collaboration and participation by CEFCA, the IEC, and Universidad Complutense de Madrid, and also some researchers that are participating from Universidad de Valladolid, from IAC and IA. The main responsibility for the consortium is the science case, also the instrument and the science ground segment. And as you can see in this organization chart, we are very intimately linked to the activities of ESA. And I have to say that over this year and a half, we have managed to get a really solid link of collaboration. We don't feel like ESA versus the consortium. We all very much feel like ARRAKIHS. I also want to highlight that this is a mission in which young people, early career researchers, play a key role. And I want to highlight the role of Alex Camazon. He's a graduate student, and he's also the instrument scientist of the entire mission. And this is, again, because it's the young people that is driving with their enthusiasm, their commitment, much of the work that you will see here in the mission. And also, we see this as a training opportunity that within 10 years of the mission, you actually have the next generation of leaders of future M and L class missions at ESA. The schedule is very fast, so you can see on the top the spacecraft timeline and on the bottom the payload. We passed phase 0 of the payload in September last year, and only 4 months later we passed phase A. And to the best of my knowledge, I think that we were the fastest ever mission in the history of the European Space Agency to pass phase A in only 4 months. And with huge congratulations from Frédéric Safar, who is the head of the new divisions, of the new missions. I also want to say, because I think it's important for all of you to realize that Spain is leading it through the effort and the support of CTTI and the Agencia Estatal del Espacio, but also with a financial commitment. It's about 45% of the 39 million or so that the consortium is providing that is being committed by Spain. And by Spain is all of you. So what I want to say is that this is an open invitation to all of you to participate in our mission. You have open doors, and we will very much welcome your participation. Now, there are two things, I think, that qualify ARRAKIHS as an F-class mission. One is that we have a very well-focused science case that, despite being very focused, has profound consequences in cosmology. The second one is the very high technology readiness level of our technology, because from the very beginning, we joined forces with the industry. Starting with the science case, you can see here that our goal is to resolve the observed tensions of the cold dark matter model at galaxy halo scales. And you can see the example here on the right. This is the so-called missing satellite problem and the plane distribution, or the satellite planes problem, in which what you can see is simply the number of satellites that are observed in the halos of the Milky Way and Andromeda galaxy compared to the actual predicted numbers from CDM, which exceed in a very large amount what you can actually see. But of course, these are only two objects, right? Two halos, Milky Way and Andromeda. Now, on the left, you can see the study of the stellar streams. These are the distraction of some of the satellites due to the tidal forces in gravitational interaction with the main galaxy. And according to CDM, there should be stellar streams in every galaxy halo that we can see. But when you go and look at them from the ground, they can be observed only in a few. So now you have large numbers, but the problem is that you may not be reaching sensitive deep enough. It's not very sensitive. So lack of numbers, not sensitive enough, and that's precisely what we set out to do in ARRAKIHS. So what we want to do in ARRAKIHS is to provide a very, very deep, simultaneous, visible and near-infrared observations of a statistically representative sample of galaxy halos of Milky Way-type galaxies down to an unprecedented surface brightness. And you can see in this plot on the right, we're going to focus on three observables: the stellar halo, the stellar streams, and the satellites. You can see the properties that we would like to measure, and from those properties, how we can extract the implications of the physics, the physical processes, both related to the types of dark matter and also the typical mechanisms of baryon physics. I want to highlight one thing. This is the first mission, space mission, that is focused on the study of the ultra-low surface brightness universe. And in order to do that, you really have to optimize three things from the very beginning, from the design of the mission, which is the instrument, the observational strategy, and the image processing algorithms. Otherwise, it's extremely difficult with the standard observatories to actually reach the very, very low surface brightness that we want to reach. And in addition to this, we're actually carrying out an extensive set of simulations, cosmological simulations, to be able to have the proper data to compare with our observations regarding the predictions, not just of CDM with the standard baryon physics, but changing the baryon physics and also changing the flavors of dark matter. So this is in a nutshell ARRAKIHS. This is how we're organizing ourselves during the current phase B. I forgot to tell you actually that the key thing that we're doing right now after phase A is conduct everything that needs to be done in order to pass preliminary design review. This will be in spring 2026. This is the phase B. And as we expect, actually, we pass PDR, then the mission will be adopted, and they select also the spacecraft that will come along with our payload all the way to launch in 2030. So this is in a summary of what we are doing now during the phase B. We start with a particular flavor of dark matter and baryon physics. We produce the cosmological simulations from which we will extract the particular galaxy models. And then we focus on the properties of the three observables, the stellar streams, the galaxy satellites, and the stellar halo. And we define the statistical descriptors that then will allow us to discriminate between the various different cosmological simulations. Now, those galaxy models serve as the input for the mock image code that we have developed, and that also includes as another input the survey strategy. And that's where we put what is the galaxy sample, what are the typical filters, what is the sensitivity and the resolution that we need, what is the offset and detail strategy in the observations that we will take, etc. After producing the mock images in the most realistic manner, then we go through image processing to be able to derive what it is the best image so that we can do the science. And the best image requires an accurate modeling of the background, particularly stray light, so that we can remove it and then see the very, very faint features we want to study. After that, you go into data analysis, and the first thing we need to do is to remove the contamination by the foreground galactic cirri and the background galaxies. And once that we have identified statistically, we don't have a spectroscopy, we can identify the candidates to the streams and the satellites, then we characterize them with the same statistical descriptors that we have defined in theory. We compare the two of them, and from that comparison, we will be able to determine whether we can actually discriminate from the various theoretical predictions, and if so, it will define the figure of merit regarding the limiting surface brightness of our survey, the limiting magnitude, the spatial resolution, and the minimum number of galaxies. Okay, so just showing you a little bit of the work that we are doing in theory. So we're carrying out at the moment 30 very high resolution galaxy simulations in 6 different flavors of dark matter. This is work done by Santi Rocafabrega and his team both in Sweden and in Switzerland. And from this very high resolution, we will be able actually to include 2 more from the Agora collaboration, which is very important because we need to understand what is the uncertainty in those model predictions. And that means that we need to understand what is the systematics associated to the use of different codes in the simulations. So we will use Agora in order to standardize actually these results from the cosmological simulations in all these flavors of dark matter, and then we will introduce different changes in the baryon physics, particularly feedback, where it is related to the stellar feedback or to the UV background at the reionization epoch. And then we will go a step further, just extracting those galaxy potentials in order to simulate at a very high spatial and mass resolution so that we can now have a better handling of the thinnest stellar streams and the smallest satellites. Overall, this work will require of the order of 200 million hours of CPU in the high-performance computers. And again, it is a major contribution, part of our legacy of ARRAKIHS to the entire community. Now, why do we need to go to space? Well, what you have here is the state-of-the-art of the work that has been done from the ground on the stellar streams. This is the work by David, Maria Angeles, and their student Juan Miró. This is taking all the galaxies from the DESI legacy survey, and only about 10% of the entire sample actually showed stellar streams. Why? Well, they're reaching only 28.5, only, quotation marks, only 28.5 magnitudes per square arc second. If you want to test the predictions of CDM, you need to go much deeper, because the key thing when you try to measure an effect is that the size of the effect has to be much smaller than the size of the uncertainties, both on the model predictions and on the measurements. So what you can see here is the detection rate of the stellar streams on the upper right versus the limiting surface brightness of the surveys. And the lines correspond to the predictions of the CDM model. And you can also see some of the representations of our own galaxies that we have modeled in ARRAKIHS at different cutoffs in surface brightness to illustrate the point. So at 27.5, this is what you see, very much no streams. 28.5, this is the limit of Juan Miró's work from the ground. You start seeing maybe one here on the bottom left, 29.5, 30.5, 31.5. At 31.5, every galaxy that we observe, almost every galaxy that we observe, should actually show a stellar stream. And that's the simple test. And this is what we want to do in ARRAKIHS. So we want to reach 31.5 for a representative sample of galaxy halos, and the number of galaxies will determine the uncertainty on the observation. So we need about 75 or 100 objects. And then we will be able to corroborate or not CDM. Because if we only observe in about 60% of the sample, then this will fatal blow to the CDM theory. And that's where our cosmological simulations, named Harkonnen by Santi, will actually kick in, where we can actually then study, if they are not consistent with CDM and the current approach to baryon physics, what is the modifications to baryon physics, or what are the different types of dark matter we need to consider. This is just one of the statistical descriptors that we will use. We have others that we're currently defining, both for the properties of the stellar streams, the luminosity function of the satellites, the distribution of the satellites, etc. Now, the second aspect that I mentioned is the high technology readiness level of our technology that is based on the ISIM binocular camera by Satlantis, which is a company based in Bilbao. The nice thing about this camera is that it has already been validated in space. This, you can see Commander Chris Cassidy, International Space Station, that is just about put the ISIM camera in the airlock to be positioned on the outside of the Japanese Kibo module. Again, this is 2020. At this point, Commander Chris Cassidy was actually talking to King Philippe. It was a very emotional day for all of us. This is the binocular camera. It is a very simple but very powerful camera that we designed and patented at the University of Florida. It's only 3 optical elements. They're all spherical surfaces on axis, so it's relatively easy to align. But despite the simplicity, it offers diffraction-limited imaging over the entire field of view, which is 1.3 degrees, and over the entire wavelength range, all the way from 300 nanometers to 1.7 microns. So now, since the 2020s, Atlantic has validated already, has launched to space 6 of these cameras already, and there will be 3 on their own satellites and a 4th satellite that will be launched in October, mainly for Earth observations. Now, this is the current layout of the payload. You can see 2 binoculars, one in the visible and one in the near-infrared, with 4 filters. One very broad filter from 350 nanometers to about 950 nanometers for detection in the visible. Another very broad filter from 950 to about 1.6 microns. And then 2 broad filters in the extremes of this wavelength range, in the blue and in the red. That is the current configuration, no moving parts. You have the periscope, actually, to maintain the same mechanical design, and then the baffle for strelate that you can see up there. Then, in addition to the baffle, you can see these radiators for cooling down. Will be passive cooling all the way to 140, 150 Kelvin for the detectors. We'll be using the H2RG, the same one from Euclid and near-infrared. But in the visible, we're actually developing a brand new set of detectors with Teledyne, and this is a collaboration between Satlantis and Teledyne. And these are the next generation of high-performance CMOS detectors, all the way from 200 nanometers to 900 nanometers. The main problem that we're having is precisely the thermal shield, because the Earth is a huge object that is just standing below us. And maintaining the radiation field away from the radiators has been one of the major headaches that we have had so far. Regarding CONOPS, we wish with our heart that we would go to L2, but we were told very clear from the very beginning, there's no money. So we have to be at low Earth orbit at about 800 kilometers altitude. It's asynchronous, 6 a.m., 6 p.m., very much around the terminator. And the field of regard determines the solid angle over which we can actually observe our galaxies, determined by the solar angle and the zenith angle. Now, the galaxy sample, we are using a magnitude and mass limited sample, very much Saga style in the selection, plus additional selection criteria to optimize the observability. Overall, we had 226 galaxies. This is work also done by Maria Angeles. And what we have done is that we can observe these objects for about 150 hours each in exposures of 10 minutes in order to reach the desired sensitivity. And here you see a sketch of how we can do it. So we start in the first observation, target number 1. We're taking 10 observations of 10 minutes. After that, again, the Earth comes into the radiation field. We have to move then to a second object, here target number 2. We take another three images, and then we slew to the third position, and so on, and then we repeat the orbit. At 800 kilometers, each orbit is about 100 minutes, just to give you an idea. And it is very important, in each of the 3 exposures, we dither. And this is very nice because it's part of the observational strategy that I'm telling you is absolutely essential in order to be able to model the background accurately, to be able to subtract it and reach the surface brightness. So here you can see a sketch of how we're doing it. Very much, we are actually pointing the telescope at an offset from the galaxy of about 10 to 15 arc minutes. In each of these positions, let's say number 1, in each of these positions, let me see if I can start again. We're taking position number 1, take 3 dither options. Then the next orbit, we go to position number 2, which is now, again, on the other side of this circle. Then we take another 3 dither options. Then we go to position number 3, and like this all the way 300 times to cover the 900 exposures. Covering the field of view will actually move all around the circumference. And that is what allows us actually to smooth some of the defects in the camera so that we can reach the low surface brightness. Second is the mock simulation. We have what I believe is one of the state-of-the-art of the mock simulation codes to simulate missions in low Earth orbit. This is work that we started at the University of Florida, and our student Alex took it actually to the next level. You can learn all of it in his poster, and I very much encourage you to see it. Alex has been invited now twice, actually, to ESTEC because ESA was so enamored from our mock image code that they want to implement it as part of the tools that can be offered to the entire European community to plan the next low Earth missions. It includes everything. We know intimately the camera. We built it. We have already tested in the lab, from the point spread function to the ghost images to the flat fields. The same thing goes to the electronics. We included both solar system effects, of course, the Earthshine, very, very important. We include the effects of the galactic cirrus, stellar fields, and all the whole background. Okay, so I will have to go a little bit faster. Then, after we have produced a set of 900 images that most realistically actually reproduce the actual observations with ARRAKIHS, then we go into the algorithms for image processing. This is what we call M&M, or Mohammed's magic, because it is absolutely impressive what he can do actually with the set of images that we're providing. And it is not trivial. We start with the offset and dither field because we are now offsetting the image. It will be about 2 degrees diameter. The central 1 degree is the deepest part. That's what we are concentrating in. He will first model the second order stray light associated to the ghost images and to the Earthshine. After doing that, then he will be left with the gradient of zodiacal light, which is by far the main contribution to the background. And after he models and removes the zodiacal light, then we have the point spread function. And that's where the work by Raul has been also absolutely impressive. And you can see in this animated GIF how he is able actually to model the PSF, and including the extended wings, and subtract the very crowded field so that now you can gain the contrast for the very low surface brightness features that we want to observe in ARRAKIHS. Overall, we produce this image. And from this image, we derive the limiting surface brightness, which is 31.6 magnitudes per square arc second in the visible and 31 in the near infrared. Again, unprecedented at this level. And I remind you, it is a small camera, only 15 centimeters diameter. And this is a type of science that you can do with the small telescopes in low Earth orbit, and that may open up a new era of discoveries from space. Once that we have the image, now we go into the analysis. And just to finish, just to tell you the work that Elena has been doing, this is just a small patch of the field of view with the segmentation map obtained from GenoAstro. This is just to give you an idea exactly the type of satellites that we're dealing with. So it's tiny little blobs actually in our image. And just to give you the preliminary work by Elena on the completeness functions in the 4 filters. So with this, I just finish saying there's a lot of work to do in order to complete phase B. I'm just listing some of the tasks that we have to do, both in the instrument, on the science and the science ground segment. But I hope that by the next meeting at SEA, 2 years from now, I can actually share with you all the good news that our mission passed phase 2 and that has been formally adopted to be the next F-class mission of the European Space Agency. Thank you.
So, it's time for 2 questions. We can have 2 questions. I cannot see. Here there is 1 question.
Hi, Rafa. Thanks for the talk. My question will be short because you have a very short time from now to launch date, so you have to work a lot. This is a question out of total ignorance, but I have seen in the fields that you have shown that they were quite populated by stars. Is that a problem, and the fields have been chosen in purpose with this crowdness, or?
Yes, so you're completely right. I mean, stellar component is one of the key contaminations that we have. But we have 226 galaxies within our sample. We only need 75 to 100 to complete the statistic study. So we can actually select our galaxies mainly that they will be away from bright stars. The problem with the bright stars are, of course, the effect of the extended PSF to much larger area, and also the ghost images, because we do have internal reflections in the camera. So this is something that we're doing now in collaboration with Maria Angeles in order to see how we can optimize the outcome by biasing the final sample towards those that will not have really bright stars, not just inside, but also close to the field of view. The other stars can be accurately, as Raúl has demonstrated, modeled and subtracted, and it's actually impressive how well it works. Thank you.
Thank you. Maybe I have a question that is almost mandatory to both of you. The idea is a lot of people working in Euclid, a lot of people working in ARRAKIHS, very common goals in some sense, so they're matter nature. The question is, can the science of ARRAKIHS be modified during these 5 years, expecting the first results of Euclid? Or do you have some working groups working in common? Can you explain just quickly on that, but interesting?
Yes, so let me see, perhaps I can show you something. So first of all, I mean, we come in the wake of Euclid, the major cosmology mission at ISA. And of course, just this. And of course, you can see the beautiful images. It's extremely difficult to compete with Euclid on point sources. It's unbeatable. However, we are focusing on surface brightness, and that is the complementarity between the two surveys. So what we have done, there are about 2/3 of the people in ARRAKIHS are already working in Euclid. We actually started a joint team that is sponsored by the Space Institute in Switzerland, so that we are going to be working on the complementarity of ARRAKIHS and Euclid, and also how we can help to improve even their analysis of the local universe. They can do a fantastic job actually in the local universe. But even in the first meeting that we had, you can see the comparison between the published values in surface brightness, this is Jean-Charles Quilland paper, and the current values that we are deriving. And again, the goal is about to reach of the order of a factor of 10 deeper than Euclid in the visible, and between 15 to 25 times fainter in the near infrared. And here just a very quick just comparison of the same galaxy on the bottom, how it could be seen with Euclid and with ARRAKIHS. And again, how important it is just to go. But we're collaborating together, and our goal is to show this in a joint paper that hopefully we can publish in summer next year.
Thank you very much. Thank you. Thank you again to Rafa.